Welcome back. Now we're going to look at the naive Bayes problem again and see what other problems we can turn up that we can try to fix. So here we're looking at the weather data set. If you recall, the weather data set has 4 input variables: outlook, temperature, humidity, windy, and a specific outcome that we're trying to predict, which is whether we're going to play golf given those conditions. From last time, we took all of the tables that we compiled for our likelihood, and we said that these are the model representation that we have for naive Bayes, basically our model H theta. So let's go ahead and apply naive Bayes again at test time. Here we're going to use a very similar test instance, except that we're going to substitute sunny for overcast. As before, we're going to take these 4 conditions of the outlook, temperature, humidity, and windy as a joint event. And what we're going to do is we're going to make the naive assumption that each of the input features is independent of each other. So we're going to have 4 conditional probabilities to multiply together, plus the prior that we're going to use to assemble the probability. We can see what these entries are at the bottom. We see yes and overcast is 4/9. Play golf equals yes and cool is 3/9. Play golf, high humidity is 3/9. And windy equals true with playing golf is 3/9. So we're just going to go ahead and copy all of that information into here. 4/9, 3/9. 3/9, 3/9, and then the prior probability, which is 9/14, which works out to roughly 1%. Now let's look at the no case. And right away we see a problem with this particular probability here, right? The probability of forecast given no, because we actually have never seen a case where we actually went to play golf when it was overcast. So that might come to a problem. We're going to see how we're going to work that out. So just going through the rest of the particular cases here, we have cool equals in the case of no, high humidity and not playing golf, and it being windy outside and not playing golf. So we're just going to go ahead and write down all the probabilities here again. Times 1/5. Times 4/5 times 3/5, and then the prior of not playing golf is going to be the rest of the cases, which is 5/14. And of course, any multiplication against this term, which is 0, is going to give us 0. We can go ahead and normalize everything together as we did before, and we'll end up with something like this. So what's the problem here? It's not that we actually wouldn't conceive of playing golf when it's overcast. It's just probably the fact that our data set is a bit limited. We haven't actually gone to play golf enough times to observe the case when it was overcast outside and we decided not to play golf. We wouldn't say that it's impossible that's the case, just that our data set is too small. So in some ways, the 0 probability case of it being overcast outside when we decided not to play golf is not quite accurate. It's just an artifact that we'd say of sampling. To put this in starker terms, let's take a look at another case. Let's go to a case of rolling the die, just one time. Let's say it lands on the number 5. If we compute from a maximum likelihood point of view, where we look at what data we have, we can try to predict what the next outcome of rolling the die is. Well, it's going to be exactly 1 that is going to land on a 5, because that's simply the only observation we have. But of course, this doesn't really reflect any type of useful reality, because when we see a 6-sided die, we believe something about dice in general, that most of them are pretty fair. Maybe not this particular die that you see here, but there's some probability that it's not going to be 5. maybe we'll just assume that it's a fair die, and the probability of landing on the 5 is just 1 out of 6. So what we're going to say is that our training data is not really complete. We are sampling the training data from an underlying true function f, but that doesn't mean that we necessarily have seen all of the possible cases that could happen in training. We might have just gotten a sample that doesn't represent some cases which we think are actually probable, but maybe not highly probable to occur. And say, wait, that training data is not complete. There are some unseen cases that could happen. So we're going to take some of that probability mass and discount it from the true observations that we saw and assign it to other observations that we might have been able to see had we extended the training data to a large enough sample. We're going to add 1 for each of the possible conditional outcomes. So for example, on this table here, we have 6 conditional outcomes. So for sunny, we're going to add 1 to the case where yes was the outcome. So 4 plus 1 equals 5, 2 plus 1 equals 3, 2 plus 1 equals 3. 0 plus 1, our problematic case, is now going to have a single observation, and 3 plus 1 is 4. So of course, this is also going to change the total number of observations. So instead of having 3 plus 4 plus 2, 9, we're having a total of 20 cases now altogether, and 12 of those are the case where we're playing golf, and 8 of them are the case where we are not playing golf. And our marginals on the other side also change, right? So for sunny, there are 7 out of 20 cases now, 6 out of 20 cases for overcast, and another 7 out of 20 for rainy. So now what we're going to do is propagate this information over to this slide and recalculate the probabilities. So we have probability of yes given our instance is just going to be those conditional probabilities. Probability of overcast given yes times the probability of cool given yes times the probability of high humidity given yes times the probability of windy being true given yes times our prior probability of the yes class. And you can see this here. We have 5/12 for the overcast, so we'll just put that here. And I'm just going to copy over the rest from the other slide. 4/12 times 4/12 times 4/12 times our prior. Our prior is going to be 12/20, as you can see here. And that's going to give us an outcome of about slightly less than 1%. It should be smaller because we've assigned some extra probabilities to everything uniformly in the table. Now we're going to go to do the same thing for no. We have the probability of no given the data instance is going to be the conditional probability of overcast given no times the conditional probability of cool weather given no times the conditional probability of high humidity given no times the probability of it being windy outside given no times the prior probability of no, not playing golf. And that's going to work out. And yeah, you can see this again here, our 1/8, which is this one here, times the other ones that are not on this slide, 2/8, 5/8, 4/8, times our prior is over here, 8/20. Let me write that better. That's going to work out also not much, quite a bit less than 1%. So you can see the outcome hasn't changed, but at least we have now accounted for the case of there being a possibility that we would play golf when it's overcast. So now we're just propagating all that information over to another slide so it's nice and neat for you to see. The outcome doesn't change, but at least it's being reflected that there's a probability of the unseen data being actually a possibility. So in summary, let's talk about Laplace smoothing and encapsulate everything, right? We really think of this as add one smoothing because all we're doing is taking all of the cases of all the conditional probabilities of the likelihoods and just adding one to each of those cases. That's going to take away some of the mass that we had originally had for the observed information and then put it into the case of all the hallucinated data instances that we are adding just to make the data more smooth, right? So it's discounting some probability mass and assigning it to the fake data. So actually, we don't have to apply one. We can apply an arbitrary pseudo count, some k. What does that k mean? I'd like you to think about it. What type of relationship would we want to have the k with respect to the amount of data that's collected? Right? You can think of the case where we only have one observation, like in the die rolling example, and the case where we might have a lot of data and we still want to do smoothing. And in fact, there are many, many better ways to do this type of operation. This is called smoothing in general. There's things that are more sensitive to the type of prior distribution that we might think is more probable for unseen data. Laplace smoothing that we are covering just in this part of the course represents a very, very simple, not really used so much in practice, I'd say, but a very kind and gentle introduction to the point of smoothing.